Hello, welcome back. It's been a wonderful weekend, and I'm at the start of a beautiful Monday morning. So, we're back to talk about data models. The I wanted to call the title of this episode as When Bigger Became Smarter, but I think that may not make much sense to most people. So, this is about scale of data models. So, for much of human history, progress has been tied to scale. We built larger cities, powerful machines, faster computers. So the artificial intelligence trajectory has also followed the same path. Instead of building taller towers, we have built deeper networks. In the world of AI, scale means one thing, is the size of the model. So when we talk about model size, we are referring to the number of parameters, the internal dials and switches that the AI tunes as it learns. So these parameters are what makes a neural network capable of understanding patterns, reasoning text, creating content. They are in a sense the neurons of the digital brain. So let's look at the meaning of model size. So every modern AI model proudly displays its size in its name. If you look at Llama 13B, the B stands for billion parameters. Gemma 7B, Mixtral 8 into 7B. It all sounds very cryptic, but it makes perfect sense. So each parameter kind of occupies memory space, typically around 2 bytes. So a 7 billion parameter model already requires about 14 gigabytes of GPU memory to exist. So the relationship is simple. More parameters mean more potential for understanding complexity, but also greater costs in computation and storage. So at first glance, it seems obvious. If some intelligence is good, more must be better. But like most things in technology and life, it's not that simple. So when bigger isn't better, more parameters don't automatically make a model smarter. Many parameters may contribute little to the final output. They're effectively silent. So, this realization led researchers to rethink how models use their capacity. So, if you have a large model with 14 billion parameters, and when you make a query and try to generate output, it may not use all of them. So, that's what we mean here when we say they're effectively silent. So, instead of activating every part of the network all the time, what if the model could choose which parts to use? So that's the principle of a sparse model. So you basically pick those areas of the model which are really required for this particular context and use it. So there is a very nice term to define this kind of a model. At the heart of all of this lies one of the most innovative ideas in modern AI, the mixture of experts model. So let's talk about that. Think of a mixture of experts model as a company having several teams. So each team being an expert in a specific type of problem. So when a new task comes in, only a few relevant teams are called upon to respond. So the model doesn't waste resources by activating every neuron. Instead, it routes each token or a piece of tech to the most capable expert. This selective activation enables massive models to behave like specialists rather than generalists at a fraction of the cost. So what does that mean? So if you have a model with 14 billion parameters and for your particular query or context that you have given, if you need just one or two experts to work on it, the rest of the model will be quiet and the computation we use will be only for those two experts that we require. So a leading example is Mixtral 8x7b. What does that mean? The model comprises 8 experts, each with approximately 7 billion parameters. It now makes sense, right? Mixtral 8x7b. So clear. Mix, it already says mixed experts. So you might expect that to add up 56 billion parameters. You may need a lot of memory, but due to a lot of shared components and optimization, the total comes to around 46 billion parameters. So here's the remarkable part. For every token it processes, Mixtral only activates 2 experts. That means out of the 46 billion parameters, which are already an improvement over the overall model size of 56, out of the 46, Mixtral only activates 2 experts. That means it effectively runs as a 12 billion parameter model. Why 12 billion? Remember, Mixtral 8x7b. 8 is the number of experts it has and 7 is the number of parameters per expert. So 12 billion parameters. But with the intelligence of something far larger. So it's like having a global team of consultants, but only calling in the right 2 people for each problem. It's efficient, specialized, and surprisingly fast. Let's look at quality and quantity of data. Does that mean that every model is the same? So, can you measure it by just the number of parameters? No, not really. Even with the most innovative architecture, a model is only as good as the data it learns from. You can build a colossal neural network, but if it's trained on weak or limited data, it will stumble. Smaller models trained on clean, diverse datasets often outperform larger ones trained on a lot of noise. So that's why every leap in AI capability isn't about size. It's also about data scale and data quality. So the best way to measure that scale isn't by counting the number of pages or documents or number of data points it has consumed, but by counting tokens. So the individual units of text that models read and learn from are basically tokens. So if we can count the number of tokens it has used to build this model, that's a fairly decent measure of how big the model is. So if you look at Meta's Llama series, it illustrates this very beautifully. The first Llama model was trained on 1.4 trillion tokens. By Llama 3, the dataset had grown to a staggering 15 trillion tokens. So the quality of the model should have gone up. That tenfold increase meant the model didn't just memorize more, it experienced a deeper understanding of the world's language, structure, and nuances. Next comes the cost of intelligence. So you had a model, you know how big a model can be, and you also know that bigger model doesn't always mean better. It also depends on the tokens or the quality of data. Now let's look at the cost of intelligence. Training a model at this scale demands enormous compute power. But counting machines or GPUs isn't a reliable way to measure the cost of intelligence. Because not all hardware is created equal. Some GPUs may be really good at computation, some may be less. So the more universal yardstick to use is probably floating point operations or flops. So the number of flops required to train the model gives us an idea of the cost or how much we need to spend to build a model of this size. So it measures the total number of mathematical steps, additions, multiplications, divisions performed during training. In simple terms, flops measure the computational complexity of the model's learning process. So together we have parameters, tokens, and flops. They form the three pillars of AI scale. So parameters, this is how much the model can know, tokens, which is how much it has learned, flops, which basically is the effort it took to get there. So now let's look at how this triad defines the current frontier of AI. Companies race to build large models, train them on increasingly large data sets, and push the limits of computational efficiency. But scale alone isn't the answer. A large model that isn't trained well can perform worse than a smaller, better tuned one. So a model of a billion parameters but poor routing logic, it wastes the potential. But one with limited data will never generalize well as well. So no matter how many GPUs it consumes, it's not going to generalize well. So the lesson here is not unlike life itself. Growth without direction leads to chaos. Interesting. Intelligence isn't about being the biggest. It's about learning to use what you have effectively. So let's look at the three numbers that matter for a model size. So when you read about a new AI model, don't just glance at the parameter count. Look at the three numbers that truly matter. How many parameters does it have? How many tokens was it trained on? And how many flops were used in training it? Together, these numbers will tell you not just how big the model is, but how intelligent it might be. The story of AI's growth kind of mirrors our own evolution. At first, progress came from building more neurons, more memory, more power. Now it's about building smarter. We are learning to route knowledge, to specialize, and to focus effort where it matters most. The mixture of experts, parse activation, token scaling are not just engineering solutions, they are all practical approaches. They represent a deeper truth about intelligence itself. The true understanding emerges not from sheer volume, but from efficient focus. So, that is about the size of data models. So, think through that. Not every big model is intelligent, and not every small model is efficient. So the truth lies somewhere in between. So in nature, scale and intelligence coexist in balance. A whale is a massive mammal but acts on instinct. A cow is small but remarkably clever. So in AI, we are beginning to learn the same lesson, that brilliance isn't measured by size alone, but by how efficiently energy, memory, and learning are all directed. The age of bigger is better is giving way to more mature principles. Smarter is better. I hope you enjoyed the episode. Come back for more.